All right, hello everyone. Welcome to my talk today on using Yocto to secure your device. I'm Kevin Chau. I work for Times Corporation. We do a lot of BSP development for usually third-party clients, or we work as a subcontractor for other larger companies who are trying to put together some sort of uh, Linux foundation so they can build their own apps on top of that. So that's my primary experience with Yocto. I've recently moved more into doing security-oriented tasks, like setting up secure boot of a chain of trust things for systems. So that's my foundation for how I'm tackling this today. So, okay. So the goal of the talk is to give you a relatively high overview sort of understanding of how we can analyze security for, I'm talking specifically about embedded devices and how we can think about it during development and how that changes how we decide to bring in Yocto layers to assist us in adding in security features like de-inverity or de-integrity, and how we can how Yocto also helps us with long-term maintenance and ongoing support, like rolling out feature updates, firmware updates, things like that. So looking at the major headings here on the slide, early development analysis, threat modeling. Here specifically, we're looking at what kind of threats are we worried about for our system, for our product. So if you're designing a tiny widget that needs to send up some telemetry to a big to a server every hour or something like that, and it's not super important that that data stays cryptographically secure, that's obviously a different model than if you're designing something that is working with, I don't know, for example, medical space, patient data, things like that. So specifically, unfortunately, a lot of the things I'll be talking about are implementer specific. So I have to stay relatively general, but in this case, we want to decide what's acceptable as far as impact to system, to users, and decide how we're going to mitigate any vulnerability security attacks to the system. Here for pre-production, I'm really mostly talking about supporting infrastructure, or basically all the little side things that you need to put together to help that aren't directly used by your system, but assist with development and signing of system images, like generating those sorts of intersetting with developer keys or release keys, maybe test servers, test automation servers, things like that. So let's move on to the next slide. So specifically, threat modeling. How do we know what to defend against? This is your typical problem where you can have your home security, you have a deadbolt. The bank has some giant safe vaults that's automatically locked at a certain period of time. And the tighter the security you make, the tighter the security, the harder it is to do things on your product. So I know for specifically rapid development, if you're dealing with a lot of cryptographically signed images, kind of a pain in the butt to make changes quickly. So there's some sort of balance between having a system that's super closed off that you can't modify files during runtime for doing tests or adjustments, and something that's so wide open that is a major risk when you put it out in the field, or even has major vulnerabilities even just in testing. So that helps us put together requirements and design a strategy to choose the security features we want to implement and that are most useful, critical to the product. So for threat modeling, this is a whole presentation in itself, and I'm pretty sure I saw another either ELC or Yocto Summit conference presentation on this alone. You know, Stride, Dread, Pasta, all a bunch of acronyms for just strategies for evaluating risks and attacks and determining how critical they are and what kind of damage they can do, and maybe whether or not it's easily done, how difficult the attack is, things of that nature. So again, scope is important. Reducing your attack surface is always good, but the less we have to secure, obviously that makes our jobs easier. So today I chose to look at Stride. So that's spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privilege. So we'll look at all these real quick in order. Spoofing, so that's obviously if someone's pretending to be, they could pretend to be someone they're not. They can pretend to be the server that your device is supposed to talk to. They could tell that it needs to upgrade to some new infected firmware that they themselves, your attacker has created. So that's bad. We want to make sure that any systems that we put on the field can confirm the identity of whoever they're communicating with. Tampering, so that's modifying the device. If your attacker also happens to be a user and has your device physically, changing things and getting your device to run their own changed code or modifying libraries on the system, also bad. Repudiation, that's a little, I don't see a whole lot of this, but mostly if we want to have proof that someone's changed perhaps a configuration file or something like that. I don't see a lot of this in development. I do, but I think it primarily refers more to systems that have big web applications or things like that, where you might have someone trying to constantly break into the system over the network, something like that. Information disclosure, obviously losing proprietary information, losing private information. We want to protect any data storage that we have, especially if it's got critical or secure data. Denial of service. We don't want, if you do have a device that needs to phone home or phone up to the cloud, or just needs to maybe communicate with another device, we want to analyze what impact preventing the device from communicating will have for your user. For example, if you have something that needs to communicate to an upstream server, and someone takes down the upstream server, what kind of impact does that have to your device? Should it just not function? Should it function with reduced capabilities? Things like that. So elevation of privilege is the last one. It's pretty easy to understand. We don't want attackers getting root access, because that pretty much is the end of the game as far as security. So today I'm going to be striking out repudiation, information disclosure, and elevation of privilege from the presentation, just to make things a little bit easier. And I'll be focusing with the security-minded view on the spoofing, tampering, and denial of service. So specifically with spoofing, tampering, what are we concerned about when we use Yocto? Authenticity. When we do a Yocto build, we're pulling in sources from online repositories, and we want to make sure that we're not, have some sort of DNS attack where we're pulling in from some other provider that's, providing sources that have been compromised or otherwise. And then the other aspect to spoofing is even if they're not providing perhaps modified code, they could change versions, provide version 2.1 instead of 2.0. That may cause variability with, it may compile, but runtime effects we're not going to be able to tell our code's not going to be repeatable. Our application and the system behavior is not going to be well defined. So that's another major aspect to being able to confirm that we're pulling down the same stuff every time when we do a build. Denial of service. This is a big one. If we lose upstream servers, what happens? A lot of times, or even network access, we're not going to be able to do a build. The fetcher will yell at us and tell us that it can't get access to such and such file, archive, etc. Yocto has built-in mitigations. You can do premiers. You can do, as I'll talk about later, you can generate your own local mirror of the archives that you're going to need, so that we can do offline builds, and it actually provides some nice features to let us turn off network access, so we can test that. More maliciously, DDoS attacks on either your company or wherever you're doing the build from to prevent you from phoning out, or DDoS to any of the upstream providers. I mean, it's kind of unlikely that they'll hit every one of the potential providers, but if you need to cut a build today and you can't get access to one of your sources reliably, that's kind of not what we want to have happen. We want to be able to do builds whatever we want. And lastly, beyond just preventing us from going out there and catching the sources, denial of service, again, can impact our devices once they're in the field, runtime, that sort of thing. So let's see how offline builds will help. So building using our local set of files, we won't need network access. Caveat here is we do at least need to run the build once with exterior access, so we can pull down all of the files that we need for the build and keep them locally stored. So you will need to sort that out. But once we do that, we can keep that as a master copy, so to speak, of the files and packages that we're going to need. And then we can also be certain that those won't change insofar as long as we have that folder of all the packages saved somewhere secure, somewhere where we're not concerned about data integrity, we'll always be able to do the same sort of build for our system. So particular use case where this is valuable is if you have you're working at a place that has very stringent IT controls for network access. This comes up a lot, and you can't get access to GitHub or some other Git repositories that are external to the company intranet. Having this ability, if at least you can get access for your build machine to do it once, grab all the sources that you need, and then further attempts, you'll have those ready to go sitting on the local machine. So how do we do this? How do we create this local repository of our packages? So we can use BB generate mirror tarballs. So a lot of you, we'll set these in local.conf, and you can also change your download directory if you want to, say, put it on a hard disk instead of an SSD, or put it on somewhere where you have tons of disk space if you're doing a particularly large build. So we're going to set BB generate mirror tarballs to 1, and then we're going to bitbake. I have here harden image minimal because that's the example I'll be using later on, but that's whatever your target image is for your system. And we're going to add this run only fetch to the tail end of the command. And so that'll just have Yocto bitbake specifically pull in all of the necessary packages and just store them in the download directory. And then we're going to change local.conf again, add our source mirror URL to here it says your download directory, so that's DLDR. We just want to make that match. and then we're going to set inherent own mirrors. And then I put here BB no network just one, just so that it'll fail if it does actually try to pull down an external resource. We can also remove the generate mirror toggles at this point. And then you can just build this normal. And it'll just use your local source of files instead of going online to try and fetch things from the external internet. Specifically here, nice little caveat about dealing with AUTOREV. Don't use AUTOREV. I did do an example test with this to confirm you will get a variable dependency chain failure. Source PV will tell you that AUTOREV is not okay because it's trying to do an access to external resource with BB no network on. So doing a quick search, grab through the meta layers I used for this example. I didn't see any instances of AUTOREV. If you have to use it, it's going to be a pain, but I would highly recommend that you just use. If you have your own application system specific recipes, do tarballs or things like that, and avoid the problems with AUTOREV. So offline builds, your obligations. Obviously, keeping your own local mirror is kind of a pain in the butt as far as now you're in charge of making sure that you have some gold standard of your sources for all of the packages that you're going to be building. So you're going to have to handle making sure that all those are valid and correct, which is going to probably be a somewhat Herculean task given the number of packages a pretty involved build can pull down. But this is of course dependent on how much, how deep you're going into your security requirements. If you need to audit all of the sources, where they come from, validate that they come from the source that you expect them to, things like that. So we'll look at a few of the methods we can confirm that when we pull down sources, they came from the person we expected, and that the archive is intact. Another side note, again, if you do have to update your package list, you're going to need to get external access again. So might be when you're doing this or thinking about doing this or running your first big build, you just stuff as many of the packages you think you might need. So you pull all of those down, and you're not stuck constantly adding, onesies, twosies to the package, to your image install, and then being forced to do the mirror tarball stuff again. So something to keep in mind. So for Yocto, you can verify Yocto itself with its signed keys, signed tags. I have a little example here where I verified the Not 234 signature. So that lets us confirm that what we got is what we expected from the Git repository. Other projects, larger projects, usually will have PGP signatures that we can also use. Linus kernel does, Greg Cage or Linus will have their own keys that we can validate releases against. Those are signed against the uncompressed archives, at least for the Linux kernel. I believe Mesa also has PGP signatures. But for the rest of the archives sources that you'll be using in your project, if you're using some smaller library or something like that that doesn't have cryptographic authentication, what can we do? We'll take a look at how Yocto can help us out with that. Checksums. This is kind of hopefully the projects that the sources that you'll be using for any of the libs that you'll be pulling in will have checksums available for their archives. If not, you can always potentially add your own if you're adding in a library that's not already supported with your own custom recipe. Yocto can set a SHA-256 or an MD5 sum and then that can confirm that it is do the checksum and yell at you if it's different. For other SCM tools or for Git or things like that, Yocto does support cross URL. So if you do have a separate provider, if you have a Git repository, but also have it mirrored as a archive, as a tarball, you can set the checksum validation over to tarball if you're really concerned about making sure that everything's the same, because it doesn't do the checksums on Git repositories, the checksum check. So that gets us past the threat modeling. We've taken a quick look at how some of the elements of Stride impact play into the Yocto ecosystem and play into us just doing builds. So the next step, we'll take a look at how do we start adding some, basic security features to our basic Yocto build for QEMU target x86-64, something like that. So let's jump right into it. So of course, Yocto is very customizable. We have a whole bunch of meta layers, both provided by the Yocto project and also through third-party vendors. So we can pull those in, add in things that we need if we already have a meta layer available that provides features. And obviously we want to do that because those are usually curated and have support, hopefully, and are vetted by other people. And of course, if we do use it, then we can also provide back patches, things like that, to things things that you may have changed in your own project. Give those back to the community. So for my example, I decided to use Metasecurity. Metasecurity provides a DM Verity implementation, some IMA EVM, and kernel module signing as features. And here is some little code snippet again of just starting from scratch, pulling down Pokey. Assume I checked, I did a check of all the tags that I'm pretty sure I'm just pulling down master here. So then we're just gonna add all the layers that are in Meta Open Embedded to our build. And then we added Meta OE, Meta Python, Meta Networking, Meta Perl, I think are all dependencies for Metasecurity. We'll finally add that at the end. So Metasecurity provides us a hardened image minimal with some really basic changes, adding a password to our Linux, to our implementation of Linux, so that you need to sign in with a password instead of just logging in as root with no password. So the way we do this, it's documented in the README, but we add set distro features, add security to that. We'll add that to our local.conf, and then we can bitbake hardened image minimal. And you can see here that I create the BZ image and the hardened image minimal export file. So how do we validate the authenticity after we've done our build? We have our kernel image, our root file system image. How do we make sure that when we provide that to our systems, that they haven't been modified in transit, things like that? So public key cryptography is usually the answer. We're going to assign it with some sort of key, have a signature that we validate. And then I have decided to bring up two of the typical ways I've seen how I've seen signing implemented for doing basically how a developer will get their changes built and signed so they can deploy it on a device that does have security features enabled. So we have a secure build machine where you have the private key is stored on that machine. We don't have direct access to do commands on the machine, but it will run, say it'll pull for changes or do a nightly build. And then it will do the build, and then it'll deploy those, the output images to somewhere where developers can access. I've also seen signing servers where we do builds locally on the development machine, and then we send it off to the signing server, and then we get back our images with the signature for our image signed. So we're going to do the run through quickly the secure build machine method. Let's assume we have their secure build machine. Let's create our own simple meta layer that adds some signing steps. So we only have to run one command to get our Yocto, get our build files out. So here is a quick little image of what happens when we do bitbake for an image. It's all very sort of condensed. So when we run bitbake, our custom image, we'll call it custom image signed. Do image complete is sort of the completion task before it does do populate license. And in that, it runs run do image x4, and then it also tars it as well, do image tar. So we would like to add a signing step where your secure build server is going to do sign our image with a private key. So how do we do that? So let's add our own custom output image recipe. We're gonna require the let's base it off of hardened image minimal, and we're just gonna add do image sign before do image complete, but after do image x4. All of this is just for example purposes. You'll probably want to do a little bit more work on how you handle your private keys in just this example. But we're adding a do image sign step here, and we're just using OpenSSL to generate. We're going to do a hash SHA-256, and then we're going to sign that with our key. And you can see here, it's just a snippet. We do that, bitbake custom image sign, and then we get out our 256 byte signature for our platform. And here is a little log of the log.task order. It's a nice little text file that shows us the execution of the tasks. So it's really useful if you want to slot in a whole bunch of extra tasks. Maybe you have to do some fancy Macarena stuff before you can get it signed, or you have to do some sort of crazy thing to get access to your signing server if you're going to implement signing that way. So we can see how they all run and in what order, and we can add things in as needed. So supporting infrastructure, we've made our signature file. Now we need to get those files out. So you can integrate with some sort of external CI platforms that has some sort of web interface, or it could just be an external SFTP server, SSH server that developers have access to, whatever you want to do. The important thing here is that the secure build machine, developers never directly get into and can't access the private keys. That's separation of the developer from our secure keys. So for the signing server example, quick overview, we're going to build the image, then we're going to send it out to the server, and that's going to be very implementation specific how you implement the signing server beyond the scope of the presentation. It could just be you do a restricted scope SCP, and then the signing server checks for files in the location, then signs it if it matches some certain regex pattern or something like that. Or it's maybe some fancy web API thing you push to an HTTP server or something like that. And then finally, again, same end of process. We need to get those files, signed files back to our developers so they can actually use them and test with them. So that covers basically development. And I was looking at security issues before we started the product. Security issues when we're doing development for the product. Now let's look quickly at some production and ongoing support issues. So one of the primary concerns here is we're going to be generating new versions that fix bugs, vulnerabilities, maybe you're adding new features, things like that. How do we create those images, and how do we maintain them? So some choices that Yocto provides us for making our lives easier, choosing an LTS release. There's a great Yocto project presentation, ELC 2020 presentation on what this means, what the LTS release means. Major benefit is that we're not expecting major changes to the API ABI, so we can expect that we're not going to be having some crazy changes to recipes and how they parse certain keywords, and that we can reasonably expect things to stay the same. Of course, you're going to have to always do your own due diligence. So the last major thing is looking at OTA updates. So there was a mistake in the slide before. I had meta-routed in the file-based authentication. But the two basic types here are file-based authentication, block-based authentication, where we either send a diff of files, we send new files as necessary to update our image, or we're going to send a whole big blob, binary blob of our images. And that really plays into what kind of authentication setup you have. Block-based authentication, like the Verity, where you're doing a hash tree, you're going to need to do the whole block because it looks at it at the block level. If you have something like IMA EVM, which looks at the metadata for individual files, you can use the file-based authentication update methods. Also outside the scope of this conversation, just in general places to start looking for what type of update manager, if you want one, to use for your project. So AV schemes cover that really quickly. We just package everything together. Our critical image, the kernel image, our RFS, and we put that together for our update bundle, and that whole thing gets slotted in, replace the whole basic system operating image. You know, A setup and a B setup, and we'll swap between the two. So finally, CVE management. Maintaining support means that we're checking for vulnerabilities and tracking new vulnerabilities as they come up and how they affect our system. The Yocto project has CVE check. It'll let you know how that impacts the packages used in your system. TimeSys also has its own meta TimeSys, which you can add to your project and does much the same thing. From you do a bitbake command and you'll get some sort of a report that's generated for that specific image. And then here's some further reading if you'd like to learn more. I highly recommend if you're working on something that needs to do a firmware update, looking at the Designing OS Tree-Based Systems by Sergio. And of course, the Mega Manual can answer any deep questions you have about how Yocto works.